I want to talk about two of our major thermodynamic variables that we'll be dealing with and how to recognize when they're changing. Those variables are enthalpy and entropy. Both of these have fancy names, but they're actually fairly intuitive concepts when you come to think about them. And what I want us to do is to gain a conceptual understanding of when these things are changing. There are mathematical ways to calculate that, but that's something you may encounter later on. Enthalpy in past chemistry is probably what you've come to think of as heat energy. When you did calorimetry in general chemistry, this would have been the energy change you would have calculated when things are heating up or cooling down. Enthalpy gets the variable H, and what we're going to want to recognize in a lot of circumstances is when enthalpy is increasing or decreasing. So our delta H, our change in enthalpy, will be positive if energy is taken into a system. What are some of the hallmarks of that happening? How do we recognize from a chemical equation or a process if enthalpy is increasing? The most obvious, since we talk about enthalpy as heat energy, is if there's an increase in temperature. Then obviously your enthalpy is going up. One of the other hallmarks of this happening is if you recognize one of the phase changes that we also associate with an increase in temperature. Melting from liquid to solid to liquid, evaporation from liquid to gas, sublimation from solid straight to gas. All of those, the way we normally think about them, require an input of energy. There's a way to recognize if heat energy is coming into a system. Another process that always requires an intake of energy is breaking chemical bonds, disrupting electrons from their happy state of being shared between multiple atoms. Making electrons less happy is always going to require an input of energy. Another thing we'll encounter when we get to talking about solar cells later is absorption of light. Light in the form of photons, that's energy. So if you're taking in photons, you're taking in energy, your enthalpy is going to increase. And we often encounter that when things that sit in sunlight get heated up. All of these things are often closely tied together. Entropy is a bit more complex to think about, and it's even more complex to define. But one of the kind of casual ways that we talk about entropy is as a notion of chaos or disorder. It's probably a little better in a technical sense to think about it as mixed upness or spread outness of things. So we're going to want to be able to recognize situations where the entropy, where the disorder of a system, where the mixed upness and spread outness of a system is increasing. How do we recognize if that's happening? A lot of these will sound very familiar to situations where enthalpy is increasing. And that kind of makes sense because the more energy you put into things, the more mixed up and chaotic they become. So if a system is increasing in temperature, its entropy is going to be increasing as well. You've got molecules bouncing around more chaotically. Those same phase changes associated with increases in temperature and increases in molecules being mixed up and moving about in random and crazy ways. Melting, evaporation, sublimation, as things are bouncing around more and more, they're more disordered. Another one that we'll see in a number of cases is if the number of particles is increasing, particularly the number of mobile particles. If I go from having one molecule bouncing about to two molecules bouncing about to 20 molecules bouncing about, that's going to be a more and more chaotic situation. The other one that's not always as intuitive is increasing volume. That would go along through the ideal gas law with decreasing pressure. And if this doesn't seem intuitive to you, think about how this works with phase changes. What do you do when you exert more pressure on something? You would squeeze it from a gas to a liquid and eventually into a solid. That's going to a more ordered state. And similarly, decreasing pressure, increasing volume is going to lead you more towards liquids and gases, the more chaotic, disordered states. So these are all ways to recognize, basically from some simple information about a chemical equation, if entropy is increasing. The other idea related to both of these that'll come up a lot for us is the idea of a system versus surroundings. And here, there's a profound statement that we can make, and that's that the universe, the whole universe, really has only two parts. The universe is made up of a system. For the purposes of our analyses, a system is going to be whatever we're talking about the chemical equation of, and the surroundings, which is everything else in the entire universe. If we define them that way, system plus surroundings equals universe. Here's why it's really helpful to define it this way. When we talk about enthalpy, when we talk about energy, we know from the first law of thermodynamics that energy is always conserved, that it isn't created or destroyed. So if energy leaves the system, it has to go into the surroundings. And if energy is taken into the system, it has to come out of the surroundings. So what that means is that the enthalpy change in the system is equal and opposite to the enthalpy change happening in the surroundings. My thermodynamics friends would string me up if I didn't put this tiny asterisk here and say that that's at constant pressure and volume, which is a close enough approximation for all the systems we'll be dealing with. The other thing that it's important to note here, and that sometimes confuses people, is that even though energy and therefore enthalpy are linked for system and surroundings, entropy is not. The entropy of the system can vary more or less independently from the surroundings. You may have reactions where they're both going up, or they're both going down, or where one's going up and the other's going down, or vice versa. You can't reason about one from the other for entropy the way that you can with enthalpy or energy.